Today we continue to solve our gas dynamics tasks, and we talk about point 3, Mach-area relation, which is devoted to two basically questions. One is the entropic flow inside the nozzle, and the second question is existence or possibility of appearance of the normal shock wave inside the nozzle. So these two questions. Let's start from point 1. This is a classical task where you have some flow properties in one section, any section inside the nozzle, in the inlet section or in the throat or any other arbitrary section. And we have to define flow properties inside another section. This task you already, I hope, know how to solve, but to make it clear for everyone who did not deliver work 1 yet, I would like to solve. Let's assume first case when the parameters are known on the inlet cross section. Okay, so the inlet cross section is cross section 1 on the left, and I will put some parameters. Okay, let it be first Mach number and pressure, and then we can see other thermodynamic properties. So 3.1, I will define subsonic Mach number 0.1, for example, okay, and I will define also pressure at section 1. It will be some high pressure, let's see, 10 atm, and if we are working with the geometry, we need to know how big is the area. The area 1 would be 1 meter or 1 centimeter square, no matter, just 1. Okay, hope it's visible. Yeah. And what we need to know, I would like this area 1 is our big cross section, right? And we need to see what are the flow properties in any arbitrary cross section. For example, in cross section, when area is 2 times smaller than area 1. So my area 2, cross section 2, is 0.5 or square meters, square centimeters, any unit. The most important is to understand the area ratio. So the area is 2 times smaller than the initial area. This can happen in the subsonic section and can happen also in the supersonic section. So basically we will receive two routes. One route will correspond to subsonic flow, and the second route will correspond to the supersonic flow. Let's see this calculation here. First of all, we are calculating the reference area by the throat area. A1 divided by A asterisk is some function of Mach number 1. As you know from the Anderson book, this is called area Mach number relation, presented here in in formula 1032, area ratio and Mach number at this defined area. We know that in the throat, M asterisk is equal to 1, right? I will not use this formula. Instead of this formula, I'm using appendix A, and it represents the same formula as we have, only in the numerical form. I will go to appendix A, and I will see here. And here in the appendix A, I will see that area ratio corresponds to some certain values of Mach number. Since my Mach number is already known, I will see that my area ratio A1 by A asterisk is equal to 5.8 approximately. 5.8. So what does it mean? It means that the throat area is 5.8 times smaller than my area 1 to have Mach equal 1 in the throat. Okay, so from this ratio I find what is my A asterisk. So probably it became a bit dense, so appendix A I will put here. So let's calculate. A asterisk is A1 divided by 5.8, and I will calculate here 1 divided by 5.8, 0.172. 0.172. This is my area of the throat. And now my point of interest is this area here, area 0.5. I will calculate this area ratio again. I will see that A2 divided by A asterisk would be equal to 0.5 divided by 0.172, and let's see how much. It's basically two times smaller. Okay, let's see. 0.5 divided by 172, 2.9, approximately 2.9. Okay, so this is the number I'm looking inside the appendix A. Since area Mach number relation is a square equation, so we have two roots. One will correspond to subsonic section and the other will correspond to supersonic section. I already see the closest value to area ratio 2.9. It's 2.964. And I will see that in this case Mach number will be equal to 0.2. So Mach M2 first solution or subsonic solution would be 0.2. And the second supersonic solution, I will look at the end of the appendix when the Mach number is supersonic. Okay, let's see where is 2.9, somewhere here. This is the closest value to 2.9 in the supersonic section, and I see that Mach number is 2.6. So my Mach number 2, second solution corresponding to the supersonic part of the nozzle, is 2.6. That's simple way how we can determine the Mach number. Now let's see the pressure. We had pressure 1 defined, and I would like to know what is pressure 2. In the pressure 2 also will correspond to these two solutions. One pressure will be corresponding to flow at Mach 0.2, and the second pressure will correspond to Mach supersonic 2.6. Let's see the first case. So Mach 0.2, I will calculate here this value of pressure. First of all, we are using isentropic relation at the initial state, at the initial Mach number we had. So Mach 0.1. At Mach 0.1, we can define the stagnation pressure. Since the static pressure is given, P0 can be found very easily here. So I will write that my P0 divided by P1 is equal to 1007. Okay, and it means that pressure 0, okay, at point 1, pressure 0, 1 would be my P1 was 10 atmosphere, 10 multiplied by 1007, and it's equal to 10.07 atmosphere. Okay, dimensional property. We have this stagnation pressure, and we know that flow is azeotropic inside the nozzle, so P02 would be equal to P01. And this value we already know, 10.07 atm. Now I go to already found Mach number. This is Mach number at subsonic case, this one, and it corresponds to pressure ratio of 1,028. I will write that subsonic case, case 1, is P02 divided by P2 is 1,028. And from here I find that my P2 would be equal to P02 divided by this coefficient. 10.07 divided by 1,028. And it will be very close to 10 atmospheres since our flow did not accelerate so much, so it did not spend a lot of potential energy for acceleration. 10.07 divided by 1,028. It's basically 9.8. 9.8 atmosphere. This is section 1 subsonic. Now we calculate same thing for the supersonic section. For the supersonic section, where we had Mach 2.6, I find in my appendix A 2.6. This is it. We confirm again that it's our case. It's again area ratio 2.9, right? So this is the pressure ratio, is 1995, almost 20. So let's assume it's equal to 20. So I will write that P02 divided by pressure 2 in supersonic case is 20, according to our table. And now we find P2 by the same way as we did before. I will divide my stagnation pressure by this coefficient, 20, and it's basically how much? It's 0.5, right? Approximately 0.5 atm. We can use calculator to calculate more precise, to find more precise value, but just to show you an idea, I think it's 0.5 is more than enough for the answer. So this is how we can work with the pressure, calculating the pressure at any arbitrary point we want if we know what is the area at this point. Same thing we can do with the density and temperature, just substituting the coefficients, but the algorithm, the strategy of calculation is absolutely the same. I hope it's clear. So this is the direct calculation. Another point to calculate here was calculation of flow properties in the throat. Is absolutely the same way as we did calculation at any arbitrary point. We just need to find what is the ratio. Here we know that Mach number in the throat is always equal to 1 if flow is azeotropic, right? And if it accelerates to Mach 1, in this case, if the pressure is enough for the acceleration. And static pressure, or it's also called the characteristic pressure in the throat, would be calculated in the same form. I will put here this characteristic sign, and I will write that P01 divided by pressure characteristic is equal to 189. basically very close to 2 times. And from here, I will find that my characteristic pressure would be then 0.07 divided by 189. And okay, approximately 5, but we can calculate more precisely. Then 0.7 divided by 189. Sorry, 89. 533. The same way we are calculating density or temperature. We assume that in such kind of nozzle, when the flow is isentropic, no matter if it's subsonic or supersonic, the flow is going according to the isentropic relations and can be used isentropic laws to calculate any thermodynamic properties or velocities or Mach number. The task 3.2 is when we have these flow properties and we have geometry, and we need to show if the flow can be considered as isentropic. It's basically we need to prove that no shock waves happen inside such flow, inside such a nozzle. This can be done when we analyze basically supersonic part of the nozzle, right? Because shock wave may appear only when the flow is supersonic. So flow is isentropic if the flow is everywhere subsonic in the first section of the nozzle and in the second section of the nozzle. This case is explained in the Anderson book. It's somewhere here. I will remind you just a moment. Right here, this is the case which explains subsonic flow in the nozzle, and we also can use isentropic relations at this case. And the case when the flow has shock wave inside is basically this case right here. So can happen only inside the supersonic section, right? And characterized by pressure discontinuity, which is a shock wave. So Mach number drops suddenly, and flow, especially pressure, adapts to the exit pressure. So the main condition here we may write mathematically as pressure ambient divided by pressure at the exit. If there is no shock wave, it has some limit, approximately this. I think it's this. We can now see the if my logic is correct or not. Y is equal to the reason is that is basically should be this value. It's the same value 189, but 189 is very close to value 2, and it's much simpler to divide or multiply by 2 than to divide or multiply by 189 by hand, right? Why this ratio will work? Because basically what we have is that when we have a normal shock wave inside the nozzle, Mach number after this normal shock wave is very small. It's basically close to 0. Before is supersonic, very high Mach number. After is very small Mach number. So pressure on the exit is at this side, and at this side pressure is ambient, and this is same as pressure 0, stagnation pressure, since the flow is stopped after the normal shock wave basically stopped. It's very close to 0 velocity. So the pressure is close to the ambient pressure. And it becomes similar or reverse to this definition here. How to calculate the exit pressure? We can do it using the same isentropic relations. For example, on the picture 10, 15, we see P is 6, calculated by the same isentropic solution. Let's have an example. And the best way to do this, to see this shock wave, is to have an expansion area high. So, for example, 25 as shown here. Let's see if the shockwave can appear inside this nozzle or not. So I will assume that my A on the exit is 25 times bigger than my throat area. I will take all the values from the previous calculation, all the flow properties, and 25. So my exit area of the nozzle is quite high, 25 times bigger than the throat. So it means that A exit is equal to 25 multiplied by 0.17. How much was that? 2. Let's see how much it can be with respect to the inlet area. 4.3. So it's 4.3 times bigger than inlet area. What can be? Nozzles working in vacuum conditions, for example, they have much bigger exit area than the inlet area of the chamber. And at this case, we can calculate possible isentropic pressure. I will see my ratio of pressures. It will be very high, is basically 529, right? P 0.1 by P exit is equal to 5. Okay, let's take 529, and it means that my exit pressure is taken from previous calculation, the stagnation value, 1007 divided by 529. It will be very, very small value. Basically this, 19 thousandths. 0019 ATM. Very small, right? And we see that this value of exit, okay, and the ambient, for example, we need to know also. It's a gram test, so it's 1 atmosphere. So we will see this ratio, how I calculated, P ambient by P exit. No, it should be opposite sign. P ambient by P exit is 1 divided by 0019 is basically 53 times, but 52.5 times smaller than ambient pressure. So the normal shock wave will happen. So my first attempt to write was not correct. I will need to change the sign here, more or equal than 2. Yeah, I'm always confusing this part. Don't worry, because one of the reasons of this confusion is if we go to see, for example, Appendix A, you will see it's P0 by P ratio. And if you will go to chapter 7 and see these formulas, isentropic formulas, you will see very different. You will see that it's P divided by P0, so it's opposite ratio. And this is why for me it's also a sort of confusion. And but by practice we can always see if pressure at the exit of the nozzle is 2 times or even smaller than 2 times, value smaller than ambient, then shockwave will exist. Look, P by P0, T by T0, and here P by P0. So they reverse in some parts. They reverse this formula. In other parts, it's same. For example, here is reverted. Here is original order, and in the other sides as well. We can see, we can find these reversed formulas. But okay, the most important is to understand the idea. If the exit pressure is too small with respect to the ambient pressure, for example, like here, 52 times smaller, we can clearly see that the normal shock wave will exist. What will happen when this ratio is not 2, when this ratio is between 1 and 2? Okay, can be like this also. If this ratio is between 1 and 2, the oblique shock wave will happen inside the nozzle. So small pressure variation, small static pressure variation can be found, can be solved naturally by existence of the oblique shock wave, and the big pressure variation, like here more than 2, will be naturally solved by the normal shock wave existence. So this is how we can determine will be or oblique shock wave, or will be no shock wave, or will be normal shock wave. I will probably write here no shock wave, right? This case here, if it's 1 or even smaller than 1 ratio. If it's in this ratio from 1 to 2, it's the oblique shock wave, and if we are here and going in this direction, is the normal shock wave. So this is how, and this is isentropic flow, no shock wave. This is how we determine if the shock waves will happen or not. Some part of this information is written in the Anderson book. If you read carefully, you will find some way to find this information in chapter, I think chapter 10, about shock waves in the nozzles. Okay, question 3.3. We have flow properties in one section, and we have geometry. We need to see if the flow properties in another section, knowing that the flow is subsonic everywhere. So it's basically having some kind of trick, right? If you read the Anderson carefully, you see that, as I already just showed you recently, let's go back to this chapter, that flow can be subsonic in conversion and also in diversion part of the nozzle, or can be supersonic in both. Okay, this case right here. And flow will correspond also to the isentropic relations. So if we know that flow is subsonic, we are using only first part of appendix A corresponding to subsonic solutions. This part right here, starting from here and until here. If we know the flow is subsonic, if you are asked to solve subsonic flow, no matter where it happens, on the left or on the right side of the nozzle, you use this part of the appendix. And if you are asked to calculate only supersonic part of the nozzle, you are using this part of the appendix. It goes until Mach 50, but we know that from the theory of hypersonic flow, Mach 50, at Mach 50 we cannot get the data, right? Just using asymptotic relation, because flow is not asymptotic anymore when we reach Mach 5 approximately. So until Mach 5, we can calculate easily using this table. supersonic conditions. So probably I will not show you anything in this section 3.3. I will just say if it's subsonic or supersonic flow and calculate the flow properties. You are based basically on our first example 3.1, where I showed you how to calculate for subsonic part, right? This, and how to calculate for the supersonic part. But here is defined explicitly. Okay, question 3.4. You have flow properties on one section in geometry. Calculate if the gas constant, the adiabatic constant, Cp, Cv are independent from the temperature. This question is having some relation to chapter of the hypersonic flow, which says us when flow can be considered having constant adiabatic parameter Cp and Cv, and when not. And the recommendation usually which I give to my students is the following: that temperature is a definitive criteria to know if gas constant is changing or it can be considered as the constant. It's really constant. There is a small confusion here when we are calling gas constant, but it's not constant, right? And same for a adiabatic constant and others. So the limit temperature to have these values as constants is usually 1500 Kelvin. So temperature smaller or equal than 1500 Kelvin, it means that our gamma, what else, R, Cp, Cv are constant. To understand if temperature overpasses or not this limit, we need to use relations, isentropic relations on the nozzle. For example, I tell you that we know what are the flow properties here in the section of the exit where usually temperature is small and Mach number is high. And we need to calculate maximum possible temperature in this system. Usually it happens when the flow is completely stopped, so it corresponds to stagnation temperature. So basically, we just need to calculate stagnation temperature at this section. I will show you two examples that have different initial parameters to be used for this calculation. First of all, I will show you the simplest case. It will be given a Mach number, for example, Mach number 2 is equal 4, and temperature 2 is equal, let's have 400 Kelvin. 400 Kelvin. And we also need to define the geometry. We need to know that the area here, it's area 2, is equal to 1 supersonic part of the flow. And we need to see if our temperature, stagnation temperature, T01, is bigger or lower than 1500 Kelvin. How to make it? It's a similar calculation to our previous calculation, but we go in the opposite direction. So what we do? We see Appendix A and find where is our Mach 4. Okay, this is our Mach 4 in the Appendix A, and we see 4.2 is the temperature ratio. So T01 divided by T2 is equal to 4.2. From here we find T01 is 4.2 multiplied by 400 Okay, and it's how much? 16.8, right? 1680 Kelvin, and it's bigger than 1500 K. So our flow cannot be considered with constant value of gamma, gas constant, and specific heats. Okay. If you have also given area, as I showed here, you can see until or from which section can be considered as entropic, or sorry, not as entropic, as entropic is everywhere, from which section will be considered constant gamma, R, Cp, and Cv. So we need to find the ratio, because if you remember, I will make you a very small sketch here. Okay, this is our nozzle. This is our section 2. And here temperature is small, just using other color. Here temperature is small in this region. We don't know where is subsonic or supersonic will be, but I suppose that this. And at some region, it's a hot flow, more than 1500 Kelvin, somewhere here in this region. So we can know what is this point. We will call it point 1, transition. At this region, gamma is not constant, here in orange, and inside the blue, gamma and R and Cp and Cv are constant. To know this position, we can easily calculate the ratio. Okay, let's see. We have 1680 K, and if we divide 1680 by 1500, we will see that T01 K by T1 is 1680 divided by 1500. This is our limit, and it will be equal to 1.12. And we are looking for 1.12 in the section of supersonic or subsonic section inside the entropic flow. Let's see where it is. 1.16 I have found. It's or it's one. No, it's not this yet. Is somewhere. Okay, somewhere here. This is the closest, 1.122. Okay. And we see that it's Mach 0.78. From here we see that Mach 0.78 M1, and it's subsonic, so we are in this subsonic section. Okay. And the area ratio is 1047. A1 by A asterisk is 1047. Okay. So we can find where is this area ratio exactly at which position, and we will see the coordinate at which this separation of two models can be used in one part of the nozzle. We will use not constant gas constants, and in the other section of the nozzle, in the bigger section of the nozzle, already can be used constant values. So that was question 3.4. It's a bit more extended. Usually I ask just one thing, for example, to see if this flow can be considered with constant, gas constant, and others. And another question could be to determine position at which we have this limit, constant and not constant thermodynamic properties. Not properties, sorry, constants. I don't like constant thermodynamic constant. It's looking very weird, but it's like this in gas dynamics. There is no other way to call this process. point 3.5, we have flow properties and geometry prove presence or absence of the shock wave in the nozzle. Is absolutely same that we had in 3.2, but from another point of view. So we already saw this previously. This question 3.5 is just looking from another angle to this task. Let's go to the method of characteristics. Is the method which allows us to calculate flow properties at some specific points. And here I can propose you just one task, because usually method of characteristics is not that simple as shown inside the Anderson book, especially for planar bodies. It's given in the book, and for axisymmetric bodies is not given in the book, because equations, they are not linear algebraic equations, they are differential equations, and they do not enter into program of gas dynamics. But for people who are interested to know, it's quite interesting theory and quite nice to know and to calculate using these models. I propose you just one task here. When we know flow properties in two different points of our geometry, for example, we know what is point 1, what is point 2. We already calculated before, and we need to understand what would be the flow properties on the intersection and what would be the flow properties on the wall or on the axis of the nozzle. The method of characteristics is explained quite well in the book for planar flows. So we have two types of points. We have point in the intersection of two characteristic lines, and we have point on the wall. Point on the intersection of characteristic lines are called internal points, and the point on the wall are called wall points. And depend on where is the point on intersection or on the wall, the calculation is a bit different. I hope you already have studied this section, so I can just show you the example of calculation, or see very similar example of the calculation is shown in one example in the book. In this book, they do not give the values, but there is a book which is called Solutions of Problems from the Fundamentals of Aerodynamics. I think it's very easy to find in the internet, and they give explanation, and they solve point by point this task presented here in the figure 13.7, and they show how to calculate starting from original point, how to calculate point at any point, particular point. But here I will just show you one step of this calculation. To calculate, I will need to define the flow properties at point 1 and point 2. So let's assume Mach 1 is 1.5, and the direction of the flow at point 1, since it's on the wall, will have some direction of the flow defined. Let's see, 20 degrees, for example, theta 1, 20 degrees, and at point 2, Mach 2 is 1.2, for example, and direction of the flow is of course 0. On the axis, flow is parallel to the axis, so the flow direction has 0 angle. Based on this data, we can calculate direction of characteristic lines, the angle of inclination of characteristic lines, which is given as Mach angle. Explanation about direction of characteristic lines are given here. I'm just calculating this angle from the appendix, right? Formula is this right here, 13.10, and we can calculate two lines. One line goes up, another line goes down. From line 1 we will start. Line starting from point 1, it goes down right here. It will be calculated as theta minus mu. My theta is 20 degrees, as I told you, and mu can be found or from the formula, because it's the Mach angle, or from the appendix C from the book. Here it is. Depending on the value of the Mach number, it's 1.5 in our case. Let's see where it is. Here. So our mu is 4181. So the direction of characteristic line will be theta minus mu, and would be equal to 20 minus 4181. It will be 42 degrees, okay? 42 degrees. And it will be minus 22 degrees. So this is the first characteristic line, which is going from point 1. This line here, an inclination is minus 22 degrees. So if we know position of point 1 and we know the angle, we can easily draw this line. It's straight line going down. Now let's see direction of the line from point 2. It's a line going up. Second line starting from point 2, the direction is theta plus mu. Here we used mu1 and here we'll use mu2. And the theta 1 and theta 2. Okay, theta 2 is equal to 0, so it's 0 plus mu2 we define or by formula or by appendix C. We need to see where is our Mach 1.2, and it's 56.44. Okay, I will use just 56 degrees. 56, and it's equal to 56 degrees. It's a positive angle. This line is negative angle, this line is positive angle, and definitely they will intersect at some point. It's just a geometrical question where these 2 points will intersect. Starting from point 1, point 2, they intersect at some point. And now let's calculate the flow properties at this point. I will go to see the theory of Prandtl-Meyer flow. It's not Prandtl-Meyer flow, it's the method of characteristic, but it's based on the Prandtl-Meyer flow, as you already know. And it says to us, this is the solution of crossing points, that the direction of the flow will be 1/2 of sum of two characteristic line values, and the Prandtl-Meyer function value will be a difference of two characteristic line values. So we basically need to know k minus 1 for both equations and k plus 2 for both of the equations. K minus 1 can be defined in a very simple way. It's same as, for example, k minus 3 or k minus 1 is the same because they all are on the same line. It's theta 1 plus nu 1. Nu 1 is the Prandtl-Meyer function, is a function of Mach number. So I will go back to my line 1 and will define the k minus 1. K minus 1 is theta 1 plus nu 1 is a function of Mach 1. Okay, theta 1 we already know is 20 degrees, and the Prandtl-Meyer function we find our 1.5 and this is Prandtl-Meyer function. It's 11.9. It's should be difference. 20 minus 11.9. How much is that? 8.1, right? Is 8.1. Let me know if I'm making some mistake because it's simple. Okay, so k minus 1 is this value, and now we go to see the second characteristic value, how it's calculated, is the difference basically. From the second point, it will be called k plus 2. Is the characteristic line going in positive direction, starting from point 2 is basically this denomination. Just to confirm the formula, I think it's theta minus nu1, but we just go and see. 806. Yeah, it's theta minus nu. So I will write theta 2 minus mu 2. And this is a function of Mach number 2. Theta 2 is 0, and this value is Mach 1.2, 35.6. I did a mistake already, right? In the previous calculation. Here should be not minus, here should be plus. 31.9. Oh, it's not visible for you. I will move a bit my window. Okay, so it's not negative, it's positive. And here would be negative, is minus 35.6. Okay, that's it. Going back to the formulas, page 806, we will see that direction of the flow is the average. So theta at the intersection, it's 0.3, let's call it 0.3, 1/2 of the average is 31.9 minus 35.6. (185). Okay, we'll put 2 degrees here, and it's negative, minus 2 degrees. So the flow is going a bit down. Strange. I thought it should go up. I think probably there is some kind of error, sign error, to find this value, because it should go up. It cannot go down if at point 1 flow goes up and at point 2 flow goes horizontally, so flow should continue to go up. So there is some kind of sign problem, or problem of definition of Prandtl-Meyer function. We can check it again. And then nu3 is difference, is the difference, half of the difference. And this difference would give us 31.9 plus, since it's negative here, 35.6. Okay. $33.75. 3375. And from here we can find the Mach-3 from Appendix C. We just see where is our 33. Yeah, that was correct. It's just my probably, yeah, probably that's the problem. Okay, I will discuss right now. Let's see, 3375. Somewhere here we can do interpolation, but it's also no, that's the error. It's 3, it's not 30. Point is not on the appropriate place. Okay, this is the comma. So now it becomes much better. Okay, I will make simple corrections here. So this will be not -2. This would be another value. 28, 34. No, 28 divided by 2, 14. Okay, and here is comma here. So it will be 31.9 plus 3, 56, 1773. Okay, so Mach-3 I will try to determine if it will be okay or not. 17.2, right? The close value 17.8, 1.7. 1.7 near the wall is smaller value, but between axis and the wall is acceleration of the flow, which is theoretically happening if you already have simulated the flow. Flow acceleration is happening in the middle between axis and the wall. So this is the end of calculation for the wall. If you would like to calculate thermodynamic properties, it's shown in the book how to make it. It's just apply isentropic relation there, and I would like to show you calculation of the point near the wall. For example, point this one here. At this point, point 4, I will have to define also direction of the flow. Direction of the flow, let's see, is same as at point 1, so I will write that theta 4 is equal also to 20 degrees, right? 20 was 20 degrees, and the calculation of the flow properties can be done really much easier than the previous case. This is the wall point, and we need to calculate, or we can take the same value of characteristic line K2 as we used starting from point 2. So it was minus 35.6, and it's theta plus nu 4. Or for this direction, or it's for the upper direction, maybe it should be the opposite, because it's the other theta sign convention. Let's see. So the formula is this. Okay, it's the lower one, and for the upper one is the negative. Is the negative. We can write that K is 0.4. plus 4 would be equal to k plus 2 and would be equal to theta 4 minus mu 4. Mu 4 we don't know. This is the question to solve. And direction of the flow we define by the direction of the wall. So here, let's see that mu 4 would be equal to the difference, right? Theta 4 minus k plus 2. I hope that's okay. Let's put the values here and find out. So the direction is 20 and minus k plus 2, it will be minus 35, 356. So it will be basically plus 356, 2356. Let's see in the appendix. So it's 1.9. 1.9. This is the calculation of Mach number on the wall. We just need one equation, right? And we use predefined value of the wall direction. Or if we are calculating on the axis, we are using theta equal to 0. And this is how we find out the value of Mach number on the wall using method of characteristics. So that's it for section 4. I think section 5 and section 6 we could see next time. It will be related questions as entropic flow, a calculation from one point to another using some forms of energy equation, and also the expansion waves using the Prandtl-Meyer theory.
Só uma coisa, na 3.2, para provar que tem onda de choque normal ou oblíqua, a pressão ambiente, a razão entre a pressão ambiente e a pressão de saída tem que ser menor que 2, né?
Yeah.
Menor ou igual a 2.
That's correct. So if it's smaller than 1, will be no shock wave. It will be basically expansion wave, but that's outside of the nozzle. If it's between 1 and 2, will be oblique shock wave, and if it's bigger than 2, will be normal shock wave, the worst case.
Okay.
Okay, people, let's finish for today, and have a nice afternoon, have a nice end of the week, and we meet next time.